Now, geometrically, what is the meaning of the derivative? Well, notice as delta x goes to 0, take this point B. Imagine you're moving point B closer and closer to A. And as delta x approaches 0, what is happening to these points A and B? They're getting closer and closer. And I told you in the limit, as delta x goes to 0, where is B approaching? In the limit, as delta x goes to 0, where is this point B converging on? Yeah. So in the limit, they actually become the same. In the limit, as delta x goes to 0, points A and B collapse on each other. And then you're actually calculating the derivative at a single point. Well, that's what the derivative is. The derivative is the rate of change of y with respect to x at a single point. And in the one interpretation, good, very good. If x were time, then it would be the instantaneous rate of change of y with respect to time. The rate of change of y with respect to time at an instant of time. Okay. And geometrically, how do we represent this derivative? Geometrically, how will we represent it? Yes, Ben? Ben, I'm going to have to give you an extra point for all your answers today.
I like that.
Good.
The slope of the tangent line.
Yes. When these 2 points A and B converge on each other, then you're really taking the derivative at a single point, and then the geometrical interpretation of the derivative is just the derivative at this point here, which is the point slope. If you draw a tangent line that just touches this curve at one point, this is the tangent line. The slope of this tangent line is just the derivative, which we found to be 2. Okay. So that is the geometric interpretation of the derivative. It is the point slope of the curve. Okay. Okay. Very sophisticated concept. The rate of change at a single point. And the way you get it is through this limiting process. First, you let points A and B be separated by some distance, but then you let B get closer and closer and closer to A. And you see in the limit as point B converges on point A, what is the rate of change between the 2 points? And it's the point slope or the derivative. Now, some of you mentioned the instantaneous rate of change. That's another good way of thinking about the derivative. For example, you can think of the average speed of an automobile over a certain amount of time. You're traveling somewhere between points A and B, and you measure the distance traveled over the past hour. Okay, so that would be your average speed over that hour. Maybe you travel 60 miles in an hour. So your average speed that last hour was 60 miles per hour. But you could yes?
And that's analogous to like the like rate of average. That's the average rate of change.
Right, exactly. But let me go on. And then suppose you only let a half hour elapse, and you measure how far you've gone in the next half an hour. Okay, so you could measure that. Distance traveled divided by half an hour. But suppose you let the time elapsed get shorter and shorter and shorter. You measure the average speed over the last minute, the average speed over the last 10 seconds, the average speed over the last second, the average speed traveled over the last half a second. Okay. And in the limit, as the amount of elapsed time approaches 0, then you have the concept of instantaneous speed. That's the concept of the derivative. You can think of it as instantaneous speed. How fast were you traveling at this one instant of time? And this concept is not just of theoretical interest. It's of practical interest. Because if you get in an automobile accident, what determines the severity of your injuries? It's not the average speed of your auto over the last hour or the average speed over the last half an hour. The impact is going to be determined by what? The instantaneous speed of your car in the instant of impact. That's really what's going to determine your injuries. How fast were you going when you impacted something else? And that's really the concept of instantaneous speed that matters there. That's the concept of the derivative. Okay. So you all got that now? Makes sense? Okay. All right. Point slope. The derivative is a point slope. In this example here, we calculated the value of the derivative when x equals 1 is equal to 2. Okay. Let me just test you on something. Suppose x equals 0. At x equals 0, what would the value of the derivative be? Without working it out mathematically, just using the concept of point slope. What is the point slope of this function at x equals 0? 0. Because, Heather, did you answer that? Oh, okay. Yeah, and right here at the bottom of this function, if you were to draw a tangent line right here, it would be a horizontal line. Slope of a horizontal line, 0. And is Rebecca, is that right? Yeah. Okay. So if you were to draw the tangent line right here, it would be a horizontal line. Let's just verify that mathematically. If we let x sub 0 be 0, we can plug into our formula. Delta y over delta x is equal to 2 times 0 plus delta x. Or it's equal to delta x. That's the difference quotient. And what is the limit of delta y over delta x as delta x goes to 0? Well, delta x goes to 0, so this just right-hand side is 0 as you let delta x goes to 0. Okay, so that verifies that the value of the derivative here at x equals 0 is just 0. Okay, all right. Okay. What is, let's give another point over here. Suppose we look at this point D. And D corresponds to this value right here, where x equals minus 1. From the curve, you can see that the slope of D has what algebraic sign? What is the curve doing at point D? What is the point slope? It has, okay, Ben, so the point slope is positive or negative? Negative. It's downward sloping. So if you were to draw the tangent line right here at point D, it would look like this. So you can tell that the derivative's got to be negative there. And in fact, if we work out what the derivative is, we just go back to this formula right here. Now we let x sub 0 be minus 1. Okay. So delta y over delta x is minus 2 plus delta x. And in the limit, as delta x goes to 0, the derivative is just what? Minus 2. Okay. This difference quotient right here approaches minus 2 as delta x goes to 0. So that means this part right here is the value of the derivative. So this slope here is minus 2. the rate of change of y with respect to x. It's the slope of that tangent line at point D. Okay. All right. Now, now that I've gone over what precisely the derivative is, it's the limit of the difference quotient as delta x goes to 0. For now on, when we want to get derivatives, we won't use this approach. This approach is somewhat cumbersome and tedious for evaluating derivatives. The only reason I go over it is so that you'll have a rigorous understanding of what a derivative is. And you'll understand it's a point slope of the function.